Welcome back to Frontiers in Science, a conference in honor of Professor Yang at 100. Associate Professor Craig Leung Chuan shall now chair the second half of the afternoon session of the conference.
Right, thank you. Our next speaker is Professor David Wilkowski. Actually, he works almost in the same area as one of my good friend, Chai Hui, who is the last PhD student of Yang. Professor Wilkowski has dual appointment both at University of Nice en France and the NTU in Singapore. He's a principal investigator also at the CQT, where I am, and at the Center for Disruptive Photonic Technologies, and of course, a member of Maju Lab. His research interests range from quantum simulation, quantum sensing, coherent transport, nanophotonics, plasmonic, and probably exciton polaritons. He's currently working mainly in co-atoms, ultra-cold atoms. David?
Yep. Thank you very much, Craig. Good afternoon, everybody. So my talk is about making and using ultra-cold gases. I will spend half of my time on this topic, give you a brief history of how we produce ultra-cold gases, and then give you some example, a practical example of the useless of these ultra-cold gases. And then in the second part, I will discuss about a non-abelian gauge field. So we create artificial non-abelian gauge field using ultra-cold gases as a quantum simulator. And see here, you see the connection with Yang, because Yang has studied a lot this non-abelian gauge field. So producing ultra-cold gases is in fact two techniques in sequences. The first one is related to light matter coupling. So imagine that you have an atom with a velocity v, and then there is a light field which propagating opposite direction. And then if you absorb one photon, then the velocity of the atoms will be reduced by a quantity h bar k divided by m, where m is the mass of the atoms and h bar k is the momentum of the photon. Now suppose that this photon is emitted by spontaneous emission. This spontaneous emission is random, so will not change the mean velocity of the atom. So the first researcher that observed this phenomena is Otto Fritzsche in 1933, where he deviated an atomic cesium beam using cesium lamp. In 1975, four researchers proposed to use this light matter coupling to cool atoms using Doppler cooling theory. So here you have to imagine two contra-propagating lasers, which are ready tuned, and then thanks to Doppler effect, you see that the atoms will favorably absorb the photons coming, the light which is opposite to its direction. So you lead here to this cooling. So there was a drawback here in this scheme. It's a resonance scheme, so the velocity range is actually very narrow, typically 10 meters per second, and it's much narrower than the 300 meters per second that you have for thermal gas. So in order to solve this problem, Bill Phillips has the idea to use a magnetic field in order to change the atomic resonance position in the course of atomic deceleration. Then in 1986 and 1987, Stephen Chu and Arthur Ashkin proposed two techniques also to not only to cool atoms, but also to trap them. And at the same years, they measured temperature, and they find that the temperature was much colder than what the theory was predicted. And actually, Claude Quintalugi explained why this temperature was colder. And Claude Quintalugi, Steve Chu, and Bill Phillips received the Nobel Prize for this development of cooling and trapping of ultra-cold gases in 1997. So you can say it's fantastic, you can trap, you can cool, but actually the physicists were not very happy about that because there is a key parameter here, which is rho lambda de Broglie cube. So that's the phase space density, and this phase space density was rather small with respect to unity. And in fact, that was a bit frustrating because at unity, quantum statistics takes place, and for example, you can create a Bose-Einstein condensate that was predicted by Einstein 80 years before this. And so to achieve this Bose-Einstein condensate, you have to change technique. So you take atoms which are initially done in the magneto-optical traps, then you transfer it to a conservative traps with finite height, and so such that the hottest atoms will remove the traps, and the atoms which are remaining in the traps will thermalize and form a colder and a denser cloud. So you do this technique until you reach the phase space density that you want, and then you observe Bose-Einstein condensation. That was done in 1995 by these three people, Eric Cornwell, Carl Wellman, and Wolfgang Ketterle, that received the Nobel Prize in 2001 for this discovery. So starting from 1995, basically all the techniques of laser cooling was invented, and now people are trying to find some application of ultra-cold gases. So one of the applications is precision measurement. So atoms have narrow transition, so they are excellent resonator, very stable, and thanks to laser cooling, you can have also very long interaction time. So that's the two elements that give you to precision frequency measurement. And for example, in this experiment, you have a cesium atom and you want to measure the hyperfine structure of the cesium atom. So you start with the magneto-optical traps, then you launch the atoms upward. They will interfere with the microwave cavity, and then thanks to gravity, they will go down. That's what we call an atomic front end, and will again interfere, be coupled to this microwave cavity. And then from that, you can measure very precisely this transition here at typically a precision which is given by delta mu over mu, which is 10 to the minus 16. So that's extremely good. But again, scientists was not happy, say, oh, we should do better. And in order to do better, actually, you can either decrease delta mu or increase mu. And decrease delta mu is difficult because delta mu, in fact, is proportional to the inverse of the interaction time. So it's difficult to substantially increase the interaction time, but you can change mu, and you can, for example, use optical field, and then you have much higher mu. That's what's done in the optical lattice clock, and then people find the delta mu over mu, which is 10 to the minus 18. So it means that if you have such a clock, this clock will deviate less than 1 second over the whole age of the universe. So you see, it's extremely precise. And there is two people who play an important role here, is John Hall and Ted Hench, and in particular, these two people have invented what we call the frequency comb. So it's a kind of optical gear that allows you to transfer the precision that you obtain in an optical field into a microwave field that can be then measured with standard electronic system. So there is many applications for this precision measurement. So one is a better GPS system that we use every day, and there is a more fundamental application in order to test general relativity, to test the standard model, and to also work on some cosmological problem. The second application that I would like to mention today is about quantum simulation. So quantum simulation is an idea come out from Feldman in the 80s, and then it took another typically 20 years in order that the idea of Feldman was realized. And one, I think the trigger experiment was the observation of a Mott insulator. So here, thanks to changing the interaction of the particle, you can go from a superfluid system that you can see here on the top. So here atoms are in a lattice, which are made with optical field. And so these atoms are free to move, and then you can observe in the diffraction some peak that you can see on the right. Now, if you increase interaction, atoms are somehow pinned in each lattice size, and then this diffraction pattern disappears. So here, in fact, what you have done here is a simulation of a quantum condensed matter problem that this Mott insulator was known already when this experiment was done. But here the advantage is that you have a large periodicity, and this large periodicity allows you, in fact, to track atoms side by side using optical microscope, so you can really see the evolution of the atoms and then have a better idea of the mechanism in play here. So there is many applications for quantum simulation, so I list you here all some of the applications. There is probably many more. And what I would like to do today is to discuss about topological and geometrical physics. So we see already some example in the previous talk. So what is topological and geometrical physics? It's basically imagine that you have a quantum state, and then you want to understand how these quantum states will evolve if he is immersed into a space that has non-trivial geometry. So for example, imagine curvature on a sphere or some non-trivial topology. So that's the idea. And here, actually, C.N. Yang has done important contribution in the mid of 70s. So for example, this paper in 75, where he introduced the concept of a non-integrable phase factor. So this non-integrable phase factor are written here. So imagine that you have a path, you go from P to Q, and then you have a quantum state, Cp, at P, and then you want to take the particle that follow this path, and then you want to know which quantum states you have at a point Q. And so Wu and Yang answered that the quantum state at the point Q should be the quantum state at the point P multiplied by what they call this phase factor. And then you see in this phase factor there is an integral, and in this integral there is A, and A here is the gauge field. So you just have to know somehow the gauge field in order to know what the system, how the system will evolve. But there is a difficulty here because gauge field is not unique. You can change the gauge field. That's what we call a gauge transformation. And so, in fact, scientists tell you that if you want to have something which is measurable, realistic, then the result should not depend on the gauge field, so it should be gauge invariant. And that's the case if you do a closed loop, and that's what we call now Berry phase, and Berry has developed this theory 9 years after this paper of Yu and Wang. Nevertheless, I mean, so this gauge field is bound to some limitation, so because of gauge transformation, and from that, in fact, you can have a lot of idea how this gauge field should behave. And one important example, which is discussed in this paper, is the fact that if you take the field strength and then you integrate the field strength over a closed surface here, then this integral should take discrete value here. So the field strength is just the curl of the field here. And so this discrete value, if it's non-zero, it means that there is a topological charge or topological invariant which is enclosed into this surface. So if you are in the electromagnetism, then you can say that you have here a magnetic monopole. So this idea of topological charges and magnetic monopole was not new at that time. So Dirac has also proposed using abelian gauge field. So abelian gauge field is what you have with electromagnetism, for example. And then so this monopole takes the name of Dirac monopole. And if you go also a little bit before, there was some mathematical development done by Gauss and Bonnet that showed that the curvature of a Riemann closed form is also related to topological invariance that is called the Euler invariance. So the merit of Wu and Wang in that paper is to show, in fact, that this monopole also exists for a non-abelian gauge field. So in fact, it was also recently observed in ultracold gases, not by us, by the group of Jan Spielmann in USA. So here, he used an atom, and then he dressed this atom with microwave field and RF field. And then what he observed is that there is a monopole, and then he calculates or he measures experimentally on a sphere enclosing this monopole, what will be the topological charge, and in fact, that the topological charge is different than zero, and then he moves the sphere, and then when the sphere leaves the monopole, then the topological charge is zero, as you can see in this graph here on the right. So there is also something that is interesting for us in this paper is the theorem 4. So the theorem 4 tells us that under a global gauge transformation, the phase factor around any loop remain in the same class, and the class does not depend on which point is taken as the starting point around the loop. So we want to go a little bit further here and ask the following question: is it this phase factor here depend on the starting point? So if we start from P, go to Q, is it the same thing if you start from P prime and go to Q prime? And actually, we have some answer. We'll give you 3 cases. Let's imagine a classical case, the Foucault pendulum. So you know that the Foucault pendulum will precess because of the curvature of the Earth. And then it's clear that the precession angle will not depend on the time when you start to excite the pendulum, right? So in that case, we can answer, so the two phase factors are the same. It's also true for abelian gauge field, they are the same. But it's not correct for non-abelian gauge field, usually. They are not the same, and that's because here the gauge field take the form of a matrix, and then this matrix will change in the course of the transformation, and this change of matrix do not necessarily commute. So you have to be careful on the order that you have to do this transformation. So we do the experiment in my lab using what we call a SU2 non-abelian transformation. So we have two parameters here, phi1 and phi2, and then we measure experimentally this phase factor that we call U, and then we decompose here the phase factor into the generator of the SU2 Lie group, which is the identity and the three polymatrices. And so if we do the path like A, B, and C, we have the result on top here. And if we do the path C, A, B, we have the result on the bottom. So you see that between these two paths, we are just changing the starting point, and the results are different here. So the results depend, indeed, here on the starting point. We are in a non-abelian regime. So for the expert in the audience, it exists a gauge invariant which doesn't depend on the starting point. That's what we call a Wilson loop, and that's simply the trace of this phase operator. So how we do this non-abelian gauge field in practical in the lab? So we use our ultracold gases that is shown in the center, and then we apply 3 lasers here, which are characterized by 3 Rabi frequency, omega 1, omega 2, omega 3, and each laser here will address one ground state to a common excited state. So we form here a tripod system, as is shown on the right part of my screen here. So now you can see also the interaction Hamiltonian here, and then we can diagnose this interaction Hamiltonian, and we find eigenstates that in this situation we call a Dray state, and you can see that 2 Dray states here at 0 energy and are degenerated. These Dray states, we call it dark states, because they are not coupled to the excited states, so they will not emit any photon by spontaneous emission. Now, I write H like P squared divided by 2m plus Hi, which is the total Hamiltonian. And if you do an arithmetic following in the dark state manifold, you find an Hamiltonian where a gauge field is appearing here. And this gauge field is non-abelian. What does it mean here to be non-abelian? It means that the components of the gauge field do not commute. So that's the situation we have in the lab. Now we ask ourselves, okay, we have such an Hamiltonian, and A here, in our case, is spatially homogeneous. And we would like to see the dynamics of a wave packet inside this Hamiltonian. So if you have, if the gauge field is abelian, actually it's trivial because you can do a gauge transformation and remove the gauge field completely. So you have just a trivial ballistic motion that you can have in vacuum. Instead, if A is non-abelian, then you can show that this gauge field, even if it's homogeneous, cannot be removed, and then lead to non-trivial motion. So to be a little bit more specific, let's suppose that we derive the velocity operator, as it is shown here, and from this velocity operator, we derive the force operator using the Heisenberg picture, so it is shown here. And you see that this force operator depends on P, so it means that what we have here is a force which is non-inertial, and it depends also on the cross products of A with itself. And this cross products of A with itself is non-zero only if the gauge fields are non-abelian. More or less, you can see that there is another cross product between P and A and cross A, and this means that the dynamics is transverse with respect to P, so it's corresponding to the spin Hall effect. So we do the experiment, and here what we plot is the velocity that we observe for our atoms into this non-abelian gauge field. And then what you see is that clearly it's not a ballistic motion, otherwise the velocity will be constant. Instead, what you can see here is some oscillation, which are damped as a function of time. This damping is due, in fact, to the finite temperature of the gas. So what is important is this oscillation, and we can show that this oscillation, in fact, is related to what we call the Zitter-Bewegung effect, which is a trembling motion effect in Dirac equation. So we have here, in some sense, some relativity at a velocity which is below 1 centimeter per second, whereas usually relativity occurs, of course, at velocity which is close to the speed of light. We also show that we have indeed a spin Hall effect. So what we plot here in this graph is eta minus theta naught, where eta will be the polar angle of the velocity of this Zitterbenetung effect. Theta naught will be the polar angle of P as a function of the polar angle of P. And you see that the value that we can take is only pi over 2 or minus pi over 2. So it means that these two vectors, V and P, are indeed orthogonal here, as we expect for a spin Hall effect. So now it's time for my conclusion. So we have, I show you very briefly, of course, 30 years of history of ultracold gases. So they are useful to control quantum systems, to do precision measurement, and also many-body and topological physics, as I show you more into detail. So there is a lot of Nobel Prize winners which are connected to this field. I counted 11. I'm not so sure, actually, of the exact number of this Nobel Prize winner. So in my group, we have studied the past sensitivity of non-abelian transformation. So we see that the transformation depends on the starting point. And then we have looked to the dynamics in this non-abelian gauge field. So what is the future here? For gauge field simulator, so we would like to use this system to try to find new topological invariant and new topological phases. We also are thinking of higher symmetry. So we have here about SU3 system for quark and also for neutrino physics. And we have actually recently done this experiment in our lab. So we see some oscillation, you can see on the graph here, of oscillation that look like neutrino oscillation. There's also a very exciting field is about lattice gauge theory and Yang-Mills theory. We have also here some talks about that. So here the difficulty is that if you are discussing about that, actually the gauge field is something which is now become dynamical. Whereas in our case that we have studied so far, the gauge field is static because it's imposed by the laser that we can put around our atom. But now people are slowly success to do this kind of dynamical gauge field. With that, I would like also just to give credit to my collaborators. So the three people on top are the three PhD students that work on this project, and below is the three research fellows. And I have also some collaborators on the left, and I would like to thank also CQT and MOE for funding. With that, thank you, and happy birthday. Happy 100th anniversary for Professor Yang.
Merci beaucoup. Yeah, I think as a teacher, you shout all the time, and after some time, your voice gets louder and louder. But nowadays, I've not been teaching for a long time, so my voice gets softer and softer. Merci beaucoup. Any questions, especially from the young people? You should ask questions. Maybe one of your questions might stimulate one of the professors to engage you as a future student.
Exactly.
No? Our friends from NUS High School? Think of a question. How to become a professor, maybe. Yeah, any stupid question is, I have a question from online. Can ultracold atom be used to help change the way we commute and work? If so, why and how?
Yes, of course, and I give an example, actually, is the GPS. So the GPS signal is allow you to localize yourself on Earth, and this is associated to triangularization purposes, so you need to have extremely good clock for that. And if you can increase the clock, you can increase GPS signal, so you can increase your localization on Earth, yes. So that's really a very important application indeed. Yeah,
but you wouldn't want to carry cold atoms around. So
you don't need it, because in fact, what you want is that the satellite carry the cold atom for you. You don't have to carry the cold atom yourself. Yes.
Now there's a second question. How will ultracold atom be used to predict travel time, especially from airports when commuting to other countries?
Oh, that's a difficult one.
Well, it defines the time standard.
Yeah, thank you, Craig, for giving me the answer. Indeed, time standard, so the way that we define second,
yes,
is given by an atomic transition. I give the example, but I didn't mention it explicitly, is the cesium atoms that give nowadays the second. So you can say that, in fact, ultracold atoms are used to define the second, which is, of course, very important when you commute between your work and your home, or when you do any other kind of activities, of course.
Okay, maybe one last question.
Yes.
What other oscillations do atoms in SU3 system undergo beside neutrino oscillation? Any justification?
Okay, so that's really ongoing work in my lab. So what I say, I was a bit cautious. I say it's neutrino-like oscillation. In fact, if we look a little bit deeper, to the neutrino theory, and then you try to do a mapping with our system, this mapping is not that obvious. So I will say it's still an open question for us.
Yeah, thank you. There is one last question which I didn't read, is about whether co-atom can be used in the development of modern computers and quantum computers.
Yes, of course. That's an excellent question. I will say yes. Even, in the run of quantum computer, I will say that cold atoms are not at the first place. So the first place is probably taken nowadays by a supraconducting circuit. And then the second will be ion traps. You can say that ion traps, somehow, we use also laser cooling for that. For neutral atoms, there is some progress. And I'm very optimistic, actually. And I think ultracold gases will stay on the run. And why not winning the race at the end? I'm not so sure. Let's see.
Bon. Merci beaucoup.
Merci.